Welcome back. We're going to continue our discussion on the first of the colligative properties, and that's vapor pressure. And let's get started. So what is vapor pressure? Lowering of vapor pressure is same as just first understand what is vapor pressure. Okay. So here's a picture, right? So let's say you have this flask on the right, okay, and then you either heat it or just leave it be. Molecules constantly go from the liquid phase to the gas phase, okay? So assuming, let's say we are heating it, so there are some molecules in the liquid phase that are now going into the vapor phase. And the molecules that are in the vapor phase constantly ping around themselves and with the walls of the container, leading to some sort of pressure, okay? Now, ideally, you wouldn't eat something with the system closed, but it's just shown to actually really show you what vapor pressure means, okay? So you see these molecules in here. All of these molecules about this line corresponds to molecules in the vapor phase. That is, it's not in the liquid phase, which is this in the below. So they go from liquid phase to the vapor phase, and this area here in the flask, there seems to be some kind of pressure building up. And this is called vapor pressure. These molecules in this phase here, they collide with themselves and with the walls of the container, creating a pressure, and that's called vapor pressure. We can increase or decrease it by modifying the solution in such a way that we can either increase the vapor pressure or decreasing the vapor pressure, okay? And along those lines, I do want to remind you that a solution, okay, is solute plus a solvent. We've learned that, just want to remind you, because that's an important concept that we will get across throughout, okay? A pure solvent is just a solvent by itself. It's absolutely pure with no adulteration of any kind. But a solution is solute plus solvent. So by adding or removing a solute, or how much we add of it, we can affect the vapor pressure, and that's what we're going to learn. Okay, so before I put this one up, I have not seen this being approached in this particular fashion when this material is taught. What I have done here is I have remember I said how we can affect the vapor pressure based on the solute that we add to the solvent. I split the topic of vapor pressure into three components. One is you're adding a non-ionic solute or non-ionic compound as a solute. Remember, solute is always small quantity compared to a solvent. So a non-ionic compound, and then a compound containing a metal, and then solutes that are volatile. That is, it can easily evaporate. So we would look at vapor pressure of solutes from three different perspectives. So the first one is, what if I added a non-ionic compound to a solvent? How do I know my compound is non-ionic? Well, we went over this in 170. If your compound doesn't contain any metals in group 1, column 2, or any of the transition metals, chances are your compound will rarely ever be non-ionic. Will rarely ever be ionic, so which makes it non-ionic. Okay. So this is Raoult's law, which states vapor pressure of a solution equals vapor pressure of pure solvent multiplied by the mole fraction of solvent. I have defined what those are. And occasionally, I might ask you to calculate mole fraction of solute. So if you can calculate mole fraction of solvent, 1 minus mole fraction of solvent will give you mole fraction of a solute. But the take home is just, this is Raoult's law, which is what we're going to use to understand vapor pressure. So here's the first problem. I put all those equations and explanations again. What is the vapor pressure of a solution that contains 150 grams of sucrose, which is your solute? And this is non-ionic because there's nothing here that indicates that you have a metal. So this is your solute, and water is solvent, right? And the vapor pressure of pure solvent or pure water is given as this. Again, you do not have to convert any of this to Kelvin or ATM, because it's not about, you don't see any temperature in here, so you do not have to convert. Besides, you do not actually use the value of temperature. So we already know P0 solvent from the problem, which is given to you as 92.5 millimeters of mercury. So if you can find mole fraction of solvent, then we can find P solution. That's what it's asking. The only problem that's a little difficult is when it is metallic, okay? But I got it to the end. So this is what we ultimately have to find. So we need to find moles of this and moles of this, then we can find mole fraction of the solvent. So 150 grams of sucrose, right? And molar mass of sucrose, I believe, is 12 times 12 plus 16 times 11 plus 22. So 342 grams over 1 mole. So you find the moles of this, and then you find 100 grams of water, right, over 1 over 18 grams over 1 mole. All of this stuff we did mole fraction even in 170. So 150 by 342 is 0.438 moles, and 100 by 18 is 5.55 moles. Now we want mole fraction of solvent, so that means it's 5.55 moles divided by 5.55 plus 0.438, right? That's total moles. Mole fraction of solvent, we're not asking for mole fraction of solute, right? So 5.55 divided by 5.55 plus 0.438 is 0.926. So now to find the vapor pressure of solution, it's basically 0.926 times 92.5 millimeters of mercury. So that'll be 92.5, 85.7. Okay, so the problem is done. That's how you do it. You notice that there's a relationship that I said the vapor pressure of the pure solvent is 92, right? Just water by itself. But when we add sucrose, the vapor pressure is lowered, right? So generally, higher vapor pressure means higher vapor pressure means lower boiling point, okay? Lower vapor pressure means higher boiling point. What it really means is water would boil probably faster than water with sucrose. When you lower vapor pressure, you're taking the substance longer to boil, which is why higher vapor pressure means lower boiling point. Lower vapor pressure means higher boiling point. We will come back to this again and again throughout the course, but I want you to know how the effect of vapor pressure is. So when you lower the vapor pressure, it's going to take a lot longer to boil. So lowering vapor pressure means higher boiling point. Higher vapor pressure means lower boiling point, means it boils quickly. All right, I'll see you back with another video.